Okay, welcome to AP Chemistry. This is the first lecture video that you're going to watch, and there will be a lot of these this semester. That's my plan anyway. This first set of notes, really the first couple of weeks, they're going to be review. So use your discretion as far as, what of this you listen to. If you look at the notes and you look at the PowerPoint and you feel like, I know this, then you might be able to save yourself a little bit of time here. But the thing is, you have to have this foundation. You have to know this stuff before we move into the next stuff that we're doing. So we're basically going to rush through about an entire year's worth of beginning chemistry in about 3 weeks. So just to make sure you're back up to speed on all that stuff, and then we'll get into some of the new stuff. This first lesson is very elementary. It's just to kind of get you used to the video lectures and how they work and stuff like that. So hope you enjoy this. Try not to fall asleep. I find that slapping myself in the face really helps when I start to fall asleep, or rolling down the car window and letting the cold air in. But you're probably not watching this in the car, so that doesn't work very well. But anyway, let's move on. Scientific method. We didn't talk about this a lot last year, but we're going to be using this quite a bit. So the scientific method is basically just a way to approach problems where you're systematically, step by step, here's how we're going to solve the problem. Now, it does not have to be the same set of steps each time. Okay, it just depends on what you're trying to solve. So typically you have some sort of facts and you're observing them. So you're going to start there with the facts, okay? And then you're going to try to find patterns in those facts, trends, things that are the same every time, and then you're going to get to some sort of model. Okay, so this is sort of your hypothesis about what happens all the time, and that'll lead you to a theory. Now, you're going to test, retest, you're going to have other people retest and stuff like that. But ideally in science, we start with the information and we figure out what's going on based on what we see, what we observe. Okay, that's ideally. All right, so an example of this, June 30th, 1908 in Siberia. There was an explosion, and don't ask me how they figured this out, but they're saying the explosion was equivalent to about 15 million tons of TNT, maybe based on what it destroyed. So the hypothesis that they came up with is that a comet or a meteor or something like that from outer space hit the Earth. Well, the problem with that theory is that when they went to investigate the site, they didn't find a crater. And you would expect if a comet or a meteor hit the Earth that there would be some sort of big crater there where it hit. Well, their new hypothesis, because there's no crater and because there's really no other way to explain the kinds of elements that they found in that area, they decided the meteor must have exploded above the ground. And so it didn't make a crater because it exploded before it got to the ground. So that's an example of the scientific method in action. Okay. All right. Chemistry, this is very basic stuff. It's the study of matter and the changes that matter undergoes. In other words, matter and energy. It takes energy to change matter. Okay. These are the three states of matter down here that are being showed: solid, liquid, and gas. There's also plasma. I know a lot of you really liked plasma last year. We'll talk about that a little bit, but not much. Matter, anything that has mass and takes up space. You know that definition from probably 5th grade science. I don't think we need to talk about that too much. Atoms, we talked about this last year, the building blocks of matter. So all matter is made up of these atoms and different combinations of these atoms. You can have something like oxygen, O2, which is just a diatomic molecule. You can have water, which is a compound, H2O. You can have carbon dioxide, also a compound, CO2. Or you can have larger molecules like ethanol, ethylene glycol, aspirin, that are combinations of a bunch of different things. Now, most of these, the ethanol, ethylene glycol, and aspirin, are carbon, hydrogen, and oxygen combined in some way. Each element is made of the same kind of atom. So if you have an element, like a copper, sheet of copper, that's all made out of copper atoms, obviously. Again, this is very elementary stuff. And then a compound is made of 2 or more different kinds of elements. So again, with water, carbon dioxide, H2O, CO2. In water, you have hydrogen and oxygen combined. In carbon dioxide, you have carbon and oxygen combined. States of matter, we talked about that just a little bit a second ago, but we talked about that in detail last year. I don't think I need to talk about it a lot right now. Gases, the particles are spread out, they're far apart, they're moving fairly rapidly, and they don't really have much attraction for one another. Okay, that's a gas. Liquids, the particles have attraction for one another, so they're fairly close together, but they are able to slide past one another. Okay, and then with the solid, they have very high attractions for one another, and they're in very structured patterns. They can't slide past one another. They're held very rigidly in place. Okay, and the way to get from one to the other, if you cool or compress, then you're going to change a gas into a liquid. If you heat a liquid or reduce the pressure over a liquid, then it can change into a gas. To go from a liquid to a solid, you can cool it. To go from a solid to a liquid, you can heat it. Okay, pressure doesn't do a lot as far as solids and liquids are concerned. All right, so classification of matter. This is all the different classifications that we have. Now, I think on your sheet here, there are some things that I want you to write in as far as examples. Okay, so you start with matter. That is the big overarching classification that we have. Anything that has mass and takes up space is matter. Okay. Is it uniform throughout is your first question. In other words, can you see the individual parts, or does it look like just one thing? Okay. If the answer is yes, it's uniform throughout, then you're going to call that a homogeneous mixture. Okay, or a homogeneous something. Okay, we don't know exactly whether it's a mixture or a compound yet. An example of that would be salt water. Okay, and that's one of the things I want you to write in there. If the answer is no, it's not uniform throughout, then we're talking about a heterogeneous mixture. Example of that might be mud, salad dressing, different things where you can see the individual parts mixed together. Okay, now if it is homogeneous, does it have a variable composition? And what variable composition means, in other words, are there a couple of different things in there that you could separate out physically? Okay, and if the answer to that is yes, then we've got a homogeneous mixture. Okay, this is not a compound or an element. This is actually a mixture, but it's a good mixture, so it's homogeneous. It's uniform. And an example again of that would be salt water. Okay, now if the answer is no, it does not have variable composition. In other words, everything that's in there is exactly the same. They're all water molecules. Okay, then we're going to call that a pure substance. Okay, and so that's the difference between a mixture and a substance. Maybe I should put over here, this is a mixture, and then up here this is also a mixture. Okay. So then when you know it's a pure substance, you've got to ask one other question. Can it be separated into simpler substances? If the answer is yes, it's a compound. Okay, and again, example of that would be water. If the answer is no, then it's an element, and that would be oxygen. Now, elements can be separated into simpler substances, we know that, but if you separate oxygen into simpler substances, now you just have protons, neutrons, and electrons. It's no longer oxygen. Okay, you've actually changed it into something else. So, yes, elements can be separated into simpler substances, but if you do that, you change the composition of the material that you're working with. Okay, mixtures versus compounds. This is pretty simple stuff. Again, so we've got atoms of an element, molecules of an element. This is showing, for example, like a diatomic molecule. Here's some examples down here. We're going to talk in a couple days about how to remember the diatomics. Molecules of a compound. That's all of these right here. And then you've got mixtures of elements and compounds, and that's when you have several of these things mixed together. Like you have an NH3 molecule right here, and you have an H2O molecule. No, they don't have any H2O molecules in there. They have, looks like, maybe N2 molecules in there. And then you've got either some helium or some neon atoms in there, all mixed together. Okay, and they're not chemically combining, they're just in the same space, so we call that a mixture. Okay, and that's the difference between elements, compounds, and mixtures. And then again, we're going to talk more about the diatomic molecules in a couple of days. Okay, Properties and changes of matter, real quick. Properties of matter. If you have physical properties, you cannot change the compound or element into another compound or element in order to observe those, okay? So boiling point is an example because if you boil something, you're just changing it from a liquid to a gas. You're not changing what it is. Density is the same way. You can measure that without changing the composition. Mass, volume, all of those things you can measure without changing the composition of the material. Chemical properties can only be observed when you perform a chemical reaction, okay? And so, again, I think we're pretty familiar with the difference between physical and chemical properties, I hope. Intensive versus extensive. We talked about this just a little bit last year, and we're only going to talk about it a little bit this year because I've never really seen this show up on the AP exam. Intensive properties are independent of the amount of matter, okay? So it doesn't matter how much you have, these properties are always going to be the same. It doesn't matter how much water you have, the boiling point of water is 100 degrees Celsius. It doesn't matter, again, how much water you have, the density of water is always going to be the same if it's pure water, okay? Extensive properties, they are dependent on the amount, so mass, volume, the amount of energy that's stored in them, that sort of thing, okay? Physical changes in matter that do not change the composition of a substance. Again, that's very similar to physical properties. So if you change the state of something, if you change it from a liquid to a gas, you're not changing what it is. You're just changing the way the molecules interact with one another. Changing the temperature doesn't change the nature of the substance, that sort of thing. Okay. Chemical changes, that's going to result in new substances. Okay. All right, chemical reactions. When you do a chemical reaction, you get one substance being converted into something else. And again, I really hope all of this is just very much review right now. Let's see, compounds. Compounds can be broken down into elements. We already talked about that a little bit when we were talking about classifications. So an example of that, if you pass electricity through water, you can get hydrogen gas and oxygen gas out. And now it's interesting, if you look at this, it looks here like we're getting about twice as much hydrogen as we are oxygen. And that has something to do with stoichiometry, which we're going to talk about in a couple of days. But what really is happening here, you've got H2O breaking apart into H2 and O2, and if you balance this equation correctly, you've got to put a 2 here, and you have to put a 2 here, okay? So you can sort of see that, you can tell that there's going to be 2 times as much hydrogen produced as oxygen, and that's why there's twice as much hydrogen gas there. Okay, relative abundance of the elements, just in case you're interested. In the Earth's crust, a lot of it is oxygen and silicon, and then you've got some other things in there like calcium, iron, aluminum, and then everything else. In our bodies, about 65% is oxygen, about 18% is carbon, 10% is hydrogen. And when we talk about organic molecules and organic chemistry, you're going to see that most of the time organic chemistry involves carbon, hydrogen, and oxygen, because that's what's in living things. Okay, top 10 chemicals produced by the chemical industry. This is a little bit dated, but you can still get sort of an idea of what's going on. Sulfuric acid is number 1, and there's a lot of that made because it's used for fertilizer and a lot of chemical manufacturing. Nitrogen and oxygen also very highly produced because, again, fertilizers, and then steel and welding, you need oxygen for that. And then you've got some other things that are on this list here, and it tells what they're used for. I thought that was kind of interesting, so you guys can take a look at that if you want. Separation of mixtures. Okay, if we are going to separate a mixture, now remember, a mixture is just physical combinations of things. They're not chemically combined, so you don't have to do a chemical reaction. But there are a few things you can do to separate mixtures from one another. One is filtration. Okay, filtration separates heterogeneous mixtures, solid substances from liquids and solutions. Okay, so in other words, you're basically just dumping the liquid through a filter, and that filter is catching the solid and it's letting the liquid through, and that's how you separate the solid from the liquid. Okay, that's a really simple one. We did that a lot last year. We'll do that again this year. Distillation. I'm going to try and set one of these up for you for tomorrow, so you can see what this looks like. Hopefully I have the equipment for that. But the distillation, the idea here is, and this is, I think we talked about this a little bit last year too. If you ever get stranded on a desert island, and statistically 1 out of 2 of you will get stranded on a desert island at some point in your life, so this is very relevant information here. But if you ever do, what you need to do to get fresh water from salt water is you need to evaporate the water and then recondense it somehow, okay? Because the water will evaporate without the salt, and then when you move it and recondense it, now you have pure water. And so this is how distillation works. You've got the salt water over here in this first flask, and you're heating it up with a Bunsen burner, and then that starts to evaporate, and it moves through this tube, okay? And then this tube actually has 2 layers to it. And again, I'm going to try and show this to you tomorrow, but you've got an outside tube that's cold water is running through it, and then the inside tube is where the gas starts to condense, okay? And as it does, it starts to drip into this other flask, and now you have pure water, okay? Distillation can separate homogeneous mixtures, so like salt water or anything that you've got dissolved in the water that looks consistent or uniform all throughout. Chromatography is another one. Also separates homogeneous mixtures, and it can separate them based on the difference in solubility. Okay. Now we didn't get to a lot of this last year. We were barely talking about this at the end of the year, solubility and how well something dissolves. But we did do a chromatography experiment with Skittles, if you guys remember, where we separated some of the colors from the Skittles, and so that has to do with the polarity. I guess we did talk about polarity a little bit more. So how attracted it is to the water, how soluble it is, that sort of thing. Okay, and so that's another way to separate these colors from one another. A lot of times we'll use that when we're separating colors of inks or dyes, like in the Skittles, that sort of thing. Okay. All right, that is it for today. We're going to talk about units of measurement next time. So hope you enjoyed this video. There's lots more of these coming. I'm going to try and turn this thing off now. This is just awkward because now I'm still talking. There we go. Alright, see you next time.